Welcome to this tutorial on projectile motion. This is an extension to the SUVAT equations tutorial, and so if you haven't seen that, I suggest you watch that first. Let's begin off by saying that projectile motion, at least in real life, is going to be purely SUVAT equations in 2 dimensions. For most people, this will either mean running 2 SUVAT equations simultaneously, or running one set of SUVAT equations using vectors. Let's start off by considering the 2 axes independently. Typically, in most questions, although you should always check, the vertical axis will be the y-hat direction, and the horizontal axis will be the x-hat direction. Let's start off with the vertical direction. If we were to consider the vertical SUVAT equations, we will write down S, U, V, A, and T, as in the last tutorial, and you would be given a certain amount of these variables. But one thing you might be slightly confused about is the acceleration. If we remove these, when given the acceleration in the vertical direction, which is usually the y-hat direction, it will be the acceleration due to gravity acting towards the planet's surface. I have some values for these here. Here we have the acceleration due to gravity on Earth, TRAPPIST-1c and TRAPPIST-1d, where the later 2 are the exoplanets that are featured often in questions on my website or examples in my animations. You see here we have the Earth's acceleration, which has the value small g, which is commonly known to be 9.81 meters per second squared. Of course, if this was in a question considering vectors, and we had the y-axis acting upwards from the planet's surface, then all of these would be acting in the negative y-hat direction. You can see that quite commonly we will measure other planets' acceleration due to gravity in terms of multiples of g. This gives us a good feel for how strong the gravity is. So for example, on the exoplanet TRAPPIST-1c, the gravity is roughly 50% stronger than on Earth. Let's move on to the horizontal SUVAT equations. Once again, you would write down your SUVAT variables, and you'll come across the acceleration, but there is no reasonable value to suggest. Here, we should always assume that the air resistance, which is realistically the only thing in nature that could exhibit some sort of acceleration, and so we will assume the air resistance is negligible. And therefore this means that the acceleration acting in the horizontal direction, which here I will just denote as h, is going to be approximately 0 meters per second squared. For any realistic projectiles being fired on a planet, you should assume the air resistance is negligible unless told otherwise. Welcome to the simulated part of this video. On the left, you will see that we have a rover and some apparatus on the exoplanet TRAPPIST-1d. The rover is going to hit a block, which is going to release a ball that will slide down the apparatus before launching as a projectile. Let's play the animation. In this example, the x-axis is along the horizontal, and the z-axis is in the vertical direction. And this almost acts as a free projectile. However, there was a little bit of horizontal deceleration caused by, I believe, friction along some meshes, which I wasn't quite intending, but it still works as an example. Firstly, we have not been told anything about the displacement, although we will be considering the point of launch to be the origin. The initial velocity has been given as 3.6 x-hat plus 2.1 z-hat. the final velocity has been given as 2.7 x hat minus 2.0 z hat. And we're considering this final point to be where the ball first touches ground. We have the acceleration is minus 6.8 z hat meters per second squared. This is a rounded version of what you saw earlier on. And then finally we have not been given any information about the time either. Let's begin by working out the time of flight. Firstly, when considering the time of flight, we are concerned with when the ball leaves the ramp and touches the ground. This is completely dependent on the information in the vertical or the z-axis. So therefore, we are only going to consider the z-hat direction. We're going to write out our SUVAT. In which we have s in the z direction, which we do not care about. We have the initial speed in the z direction, which is 2.1, and then the final speed in the z direction, which we can see from up here, is minus 2.0. We shall make that minus a little bit more exaggerated. The acceleration is minus 6.8 in the z direction, and the time is what we're trying to find out. And so very simply, we choose our SUVAT equation that ignores the variable s, which is v equals u plus at. We rearrange for t, which, if you take your time, will be v minus u over a. And then we sub in our values. T is equal to v, which is minus 2.0, minus u, which is 2.1, all divided by minus 6.8, which you will find gives a value of 0.60 seconds. And we will put a square around that. Secondly, we want to find the distance travelled in the x direction, or the horizontal distance travelled by the projectile. Once again, we're going to list out S, U, V, A, and T. I remember telling you that there was some deceleration in the horizontal direction in this question, as there were some interactions that I didn't account for. This means that the acceleration is unknown, but we do have the information regarding the initial and the final speeds in the x-hat direction, which are 3.6 and 2.7 respectively. Additionally, we now know how long the time of flight is, i.e. the time taken for it to travel from the ramp to the floor, which we know to be 0.60 seconds. And we wish to find out s, the distance travelled in the x direction. Note that this is one of the key things about projectile motion questions. Often the answer to one dimension of the question, in this case the z direction, will be used to answer a question in the other direction. Let's work this out. We need to use the SUVAT equation excluding acceleration, which will be s is equal to u plus v, all multiplied by t, divided by 2. If we sub these values in, s is equal to 3.6 plus 2.7 multiplied by t, which is 0.60, all divided by 2. And this gives us a value of s is equal to 1.89 meters, or to two significant figures as the rest of our variables, 1.9 meters. Let's pull up our first answer. Firstly, we have t is equal to 0.65 seconds. This was purely what I was able to read from looking at the individual frames of the animation, and so therefore there will be some margin of error. Additionally, there would be margin of error in working out the initial and final velocities. And so, for a practical example, representing a real-life situation with non-perfect conditions, getting an answer this close is fairly good. And if we did proper error analysis, I'm sure it would come to include this answer. But right now, for a simple example, this is good. Let's bring up the answer to the distance travelled. The answer is 1.85 meters. And once again, we got the solution of 1.9 meters, which is very close. And so we can see that our SUVAT equations were very helpful in answering these questions, even when working out a non-perfect example. Let's move on to some theoretical examples. Let's start off by drawing a diagram. With these axes, we can draw on our y and x directions with the units meters, and our origin here. Our projectile is launched from the origin at the 0 or the null vector. The initial velocity is u is equal to 8x hat plus 8y hat meters per second. And so therefore, this is equal in both directions, giving us a 45-degree angle, which will look something like this. And then we will write on u is going to be equal to 8x hat plus 8y hat. We know the acceleration on the x-of hat due to gravity is minus 6.8. This is the same as trackness 1D, and that's acting in the negative y direction, showing us that this is going to be the floor along the x-axis. And then we also have an acceleration due to air resistance, which is a constant minus 1 x hat, or which could also be simplified to minus x hat. We also get told that the time of flight is 2.9 seconds. The first thing we need to do is find the time that the projectile has the largest y displacement. This may seem like a confusing question at first. Where do we even begin? This takes a little bit of a conceptual leap. If our path of a projectile looks something like this, an arc, this point here would be the largest y displacement if we drew our axes as such. What we have to do is we have to notice that this point, the y velocity is going to be 0. This means there's going to be no y velocity acting upwards or downwards. It is essentially stationary in the y direction, even though still moving in the x direction. This means if we consider only the y dimension for our SUVAT equations, we set v to 0, where we're going to write positive y to show which axes we're considering. Then we stick in our initial velocity, which we know from up here in the y direction to be 8. We know our acceleration, the y, to be minus 6.8. And we wish to find the time, and we're not bothered with any displacement. And now we simply take our SUVAT equation ignoring the displacement, which is going to be v equals u plus at rearranged for t, which, if you do it step by step, will be v minus u over a. We then sub in our values, which is going to be 0 minus 8 over minus 6.8, and we will get 1.176 seconds, and then we will simplify this down to 2 significant figures. Seems respectable here. You should typically put an answer to the same amount of significant figures as in the question. We have a mixture of 1 to 2 significant figures, and in this case I think 1 significant figure would not be precise enough. This means that at 1.2 seconds our particle is going to be at this point, and it's going to be at its highest y displacement. We don't know what that height is, we haven't been asked to work it out, but you could if you wanted to, just by solving for s. Secondly, find the velocity along the x-axis at this time. This is where the core of projectile motion questions comes in. We take the answer to something in one axis, and then apply it to a question in the other axis. Let's write down SUVAT, and we shall now write positive x for being our direction that we're considering. First of all, we know that our time is going to be 1.2 seconds, as solved before. We know our acceleration in the x direction is going to be -1. We know our initial velocity in the x direction is 8. Once again, we do not care about the distance or the displacement, we want to find v. And once again, we use the same SUVAT equation that ignores the distance, which is v equals u plus at. And this time we're just solving for v, so we sub the values in. V is equal to 8 plus a, which is -1, multiplied by t, 1.2. And this will give you that v is equal to 6.8 meters per second. This means at the time of our stationary particle in the y direction, when it's at its highest y displacement, our particle will still be moving with 6.8 meters per second speed in the x direction. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.